Hi guys, welcome to lecture 13, which is going to be amusingly titled Adventures in Matrix Land. What we're really going to be talking about today is a couple of advanced techniques that come up in linear algebra and the way that we can implement those in Mathematica. In particular, I'm interested in looking at block matrices and products involving block matrices, and in working with the singular value decomposition as sort of a gateway to other matrix factorizations. So to begin with, let's take a look at block matrices. So a block matrix is just a matrix of the form, it's a matrix of this form, right? So you have a block A, a block B, a block C, and a block D. And the idea is that the dimensions of the blocks are appropriate so that when you put these things together into a matrix, the dimensions make sense. So, for example, if A is n by n, so if A is an n by n block matrix, so if A is an n by n matrix, then that says that A contains n rows, and that means that the block that comes next to it, B, must also contain n rows. So B must be n rows, but now by m columns, so there's going to be some extra columns that are left over. Okay, so A is typically considered to be an n by n square matrix, although it doesn't have to be. So if B is n by m, well, that tells you something about what the dimensions of D must be. So the fact that A is n by n tells you that A contains n rows but also n columns, and B is n by m means B has n rows and m columns. And so this is going to mean that C, in this sort of setup, has to have columns that match the number of columns in A. So C had better have n columns. So we'll call it R rows and m columns, n columns to match A. And D, well, D is going to collect the number of rows that it has from C and the number of columns that it has from D. So C is going to be R by M, or rather D is R by M. Now, that looks really confusing when I write it down on the page. Let's just construct some matrices. So let's just define some blocks and put them together into a matrix to see what I mean about the way that the dimensions match. So we're just going to generate a matrix A, and we can do it symbolically as A11, A12, A21, A22, and if I let that be equal to A, and I look at that in matrix form, you can see that we've got a 2 by 2 matrix. Now, if I was going to put a matrix over here to the side of it, it has to have the same number of rows if that's going to be in a block. So let's define a matrix B. So B could be arbitrary, but it can have an arbitrary number of columns in it, but it must have 2 rows. So let's just define a matrix B to be a 2 by 3 matrix. So B12, B11, B12, B13. I'm thinking about these matrices as being individual matrices now, which is why I'm reassigning the index positions. So B12, B11, B12, B13, and then B21, B22, B23. And like before, I can put that into matrix form to check that I've got an actual matrix. So at this point, we have enough information that we can make a block matrix. So we could form the matrix AB. So that's a matrix that has A as the first block and B as the second block in a row together. And if we put this into matrix form, we should be able to see that this has the structure of a block matrix. Now notice we've got extra braces running all over the place when we do this, okay? Because A was a matrix and B is also a matrix, and so now we have matrices with matrices inside and lists inside of list inside of list. And so there's a Mathematica command that will take care of this for us, which is called array flatten. And if you put that into matrix form, you should be able to see that here we have the 2 by 2 block that came from A and the 2 by 3 block that came from B. So as long as the number of rows and columns are compatible when we form a block matrix like this, I can use array flatten to squeeze it down into a single matrix that I can do computations with. So just for the sake of argument, let's finish this up and do a couple more blocks here. So if I'm going to put a block C underneath this block right here, it has to have the same number of columns that A has, but it doesn't have to have the same number of rows. So let's just write C to be a row vector, or a matrix that's just a 1 by 2. So we could write C12, C11, C12. Okay, so now we have a little row. And then that's going to go right here underneath this A block. What's going to have to go underneath this B block is going to be a matrix that has the same number of columns as B, but the same number of rows as A. And that means D has to be 1 by 3. So we'll let D be the matrix D11, D12, D13. And now we're going to do the same trick where we're going to glue all this together into a block matrix. So how do we do that? Well, let's build it as a matrix first. So in the first row, I want the matrix A and the matrix B. In the second row, I want the matrix C and the matrix D. I can put this into matrix form already, and it should show me exactly what it was that I was after. Did I ever execute these commands? Maybe not. Oh, C and D are protected symbols, which is why no information showed up down there. So let's fix that. If you ever run into that before, that's actually what's going on there. Okay, so we have the blocks in the correct places. Now we're going to put it all together with array flatten. And now we see the final block form of this matrix. There's the block A, there's the block B, this is the block B, this is the block C, and this is the block D. And so this type of approach to stitching a matrix together out of constituent pieces, all of that stuff that we were saying in the book about the compatibility of the dimensions, just means that when we put blocks together, that the number of columns and rows has to be compatible so we get a matrix out and not some sort of ragged array. Now there's some commands that are useful for working with matrices. So in particular, there's an exercise that asks you to perform what's essentially actually a tensor product of a matrix, where it wants you to take a matrix and then to look at the entries of the matrix, and at each entry it wants you to insert an identity matrix and expand it. So let's just start with a random matrix. So suppose that we just pick a random integer from 0 to 9, and we're looking at a 5 by 5 matrix. Okay, so we'll call this R. And we can look at what R looks like in matrix form, just to make sure that we've got a 5 by 5 matrix here. So what we're going to do with R is we're going to use a trick that's going to allow us to replace the elements of R with matrices, because that's the point of one of the exercises in the textbook. I think 12.1 is to be able to inflate each entry into an identity matrix that has that constant on the diagonal. So what I mean by that is, instead of having 3 right here, we want to have 3, 3, 3 if there was a 3 by 3 identity in that place. Now there's a problem though if I'm going to try to use a rule substitution, which is if I put an identity matrix in here and I try to replace out these zeros, I'm not going to get what I want, because the zeros are going to multiply to 0 no matter what I multiply them by. What I'm going to do is the following. I'm going to take this matrix R and I'm going to multiply it by a symbol I. When you do that, what you've done is you've put something into each position that you can substitute except for where these zeros are. So what we could do is we could take this matrix where we've put an I in everywhere we want an identity matrix. We could replace all of the zeros with a constant array that has zeros in it, that is 3 by 3. And then we could take that matrix and we could replace every occurrence of the symbol I with a 3 by 3 identity matrix. Then let's get that looks like in matrix form. So this trick right here is basically a trick that allowed us to expand each entry with a 3 by 3 matrix. So everywhere that I had an I prior, now I have 3 times an identity. because it did the computation for me. Everywhere I had a 0, I dropped in this 3 by 3 matrix, and I did it first to make sure that I wasn't also substituting out these zeros inside the identities. And now the last step I could use, if I want to take this entire thing and turn it into a giant matrix instead of a bunch of blocks altogether. I mean, if Mathematica represents something in this way, it is a block matrix. And so you can take all of this and you can array flatten it. And if you matrix form what comes out, then you just get a matrix where you can still identify the individual blocks inside here. So that block is the block corresponding to the 3 that's been expanded by this 3 by 3 identity matrix. So this very clearly has internal block structures here that correspond to the coefficients of the original matrix. So this is one trick you can use. I will point out that there's actually a mathematical command that will let you do this, because what we've done here is actually something called a tensor product. So this is really the tensor product of this matrix R with the identity matrix. So matrix form, and then we have this identity matrix of size 3. Really what we've done here is a mathematical operation called tensoring, where we've tensored this identity matrix into this matrix, which means that in each slot we have 3 times the identity, 1 times the identity, 0 times the identity, and so on. And we can actually just do it directly, I think, with tensor product. So if we do a tensor product of R with an identity matrix of size 3, and we put that in matrix form, you can see that we have exactly the same structure that we got when we did it this way. Okay. So something to keep in mind if you have to work with these kind of block matrices in the future, and if you've spent a good deal of your mathematical career wondering what a tensor product is. On matrices, a tensor product is just a per entry multiplication where the little matrix goes inside the big matrix, or where the second matrix goes inside the first matrix. Okay, so that's some basics of block matrices and array flatten. So now let's take a look at the singular value decomposition, which is one of my favorite ideas in all of mathematics. So the singular value decomposition is a way of pulling any size matrix apart into 3 matrices that are highly structured. So basically, if you have a matrix A, you can write it as a matrix U times a matrix sigma times a matrix V, but where the V has been transposed, not wide, has been transposed. And not just transposed, but conjugate transposed. Conjugate transpose here means that you take the transpose and then you take the complex conjugate of everything on the inside. So if you're working with complex matrices, this is a well-defined operation. Now the beauty of the singular value decomposition, so the first thing you might ask is why? Why do we care about yet another matrix factorization? And the idea here is this is like an eigenvalue decomposition, but for rectangular matrices. So that's sort of the starting point. And one of the big ideas with eigenvalues is that, and we saw this in some of these power iteration methods, is that when you repeatedly apply a matrix, the eigenvalue that's the largest eigenvalue tends to dominate what you're doing. With a singular value decomposition, essentially what you're getting here is this matrix sigma, which is a diagonal matrix, or it contains a diagonal matrix where the entries of the diagonal matrix are what are called the singular values, which are actually directly related to the eigenvalues. We can do the same sort of tricks with the singular values that we do with eigenvalues. We can replace A with an approximation for A in terms of some number of the singular values, or we can use the singular value decomposition as a classifier, which is one of the prime applications in singular value decomposition is in machine learning, where we take very complicated data and we reduce it using the sort of matrix factorization into something that can be worked with. So the singular value decomposition is probably the most widely used tool that you see in undergraduate linear algebra, aside from basic operations like inverses and row reduction. So how do we compute a singular value decomposition? Well, first, let's cook up a matrix. So we can do a random matrix. Oh, I don't know. Let's pick integers from 0 to 9. Let's make the matrix 3 by 5. Okay. Put this thing in matrix form. So there we go. There's our random 3 by 5 matrix. So if I want to compute the singular value decomposition of this matrix, I'm going to need 3 variables to store the output of the singular value decomposition, because what I'd like to do is I would like to store each matrix in its own variable. So one trick you can use to do that is when you set up the variables, you can tell Mathematica, I would like U, S, and V to be stored as the variables that come out of the singular decomposition. I suppose I should name this. Let's call this T. And then this will be the singular value decomposition of T. And you know, you do this enough times and you think you know better. Get that matrix form out of there. Has no idea what to do with that. All right. So here's what the singular value decomposition looks like. Well, it's going to be angry. Right. So why did it keep all this horrible junk? Because the original inputs were integers. All right, so let's suppress this output. It'll compute us a singular value decomposition, and then let's just look at U numerically. So what is U? U is a 3 by 3 matrix. S is a 5 by 5 matrix, which is that's what contains the singular values. So you can see this number and this number and this number are the singular values of our matrix. And then finally we have this matrix V. And V is 5 by 5. So now the dimensions here are set up so that when you multiply these things back together again, you get a 3 by 5 matrix. So I have a 3 by 3 matrix multiplied by a 3 by 5 matrix multiplied by a 5 by 5 matrix. And so this entire matrix, when you multiply it out, will be 3 by 5. Now the trick is that I can get away with throwing some of this information away and get a matrix that still looks a lot like the original one. So in fact, maybe we should actually test to see how close U, S, and V get to recreating our original matrix T here. So this was our matrix T. And now let's just do U dotted with V dotted with the transpose of, sorry, U dotted with S dotted with the transpose of V. And it's mad about that, so let's feed it into numerics. And what we're going to end up with here is some extremely small numbers. So let's put this in matrix form. And you can see here that if we put T in matrix form, that these are very close. 5, 3, a number that's about as close to 0 as you're going to get with machine precision. 6, 9, 6, 5, 5, 3. Same thing here for this 0 and so on. Okay. So this essentially stored the information in these 3 matrices. There's lots of ways of testing how close we got with the approximation, but this is very, very close. So the trick with the singular value decomposition, when you're using it to reduce the complexity of a matrix or to approximate a matrix, is that instead of working with all of U, S, and V, I can reduce this problem to a problem that still will create a 3 by 5 matrix. So if I throw away some of the columns of U, so if I threw this column away, well, that column corresponds to this singular value, which is the smallest of the singular values in the SVD. And so I'm not really losing any information. So what I can do is what I think of as a horrendously cheesy trick, but one that is amazingly powerful, which is I can get almost the same as the matrix T by throwing this away, and that will get me a matrix that is 3 by 2. And if I'm trying to recreate a 3 by 5 matrix, this had better be 2 by 2. And then we're going to transpose this matrix, which means that it better be 2 by 5, which means we'll keep these 2 columns. So the trick is I can reduce this U, S, and V into smaller matrices and store significantly fewer numbers and end up with a very close approximation of the original matrix. So here's how we do that. Let's define something called U small. And U small is going to be equal to U, maybe we'll take the N of U so that we're not dealing with these crazy computational formulas that come from the integers. And then we're going to select certain parts of it. We want only columns, we want all the rows, right? So we want all the rows, but we only want columns 1 and 2. So if I look at that and I put this into matrix form, well, I don't want to put it in matrix form now because that'll define it with matrix form in it and I'll get a bunch of errors later. This thing in matrix form, I've just thrown away the third column. Now I'm going to take this little block out of S. So S small is going to be equal to the numerical version of S, but now I'm going to restrict it to entries 1 to 2 and entries 1 to 2. And I can look, that's 2 by 2. I won't put it in matrix form yet. And then finally, we're going to do a V small here. So V small is going to be equal to the numerical version of V. And now, because we're transposing this, we don't want to throw away. So we're working with V, we're always working with columns. This is actually why it's presented in this way. So even though the computation has a V transpose in it, the reason that we leave it in terms of V is so that when I'm reducing dimension, I can just think in terms of the columns and their corresponding singular values. So I'll keep the first 2 columns of V as well, all rows, columns 1 to 2. I should have a 5 by 2 matrix, which this is. I can check really fast here to see that everything is the way I want it to be by writing down U small dotted with S small dotted with the transpose of V small. And what we should find when we're done with this is that we get a matrix that is very close to the original matrix. Now notice, it's not exact. This is not a 5, it's a 3.6. And this is not a 3, it's a 2.8. This is not a 0. But you can see the structure of the original matrix in here. And the more approximation that we did, the closer we would get. And so we missed some values by quite a lot. So this particular value right here, we've lost a 6 down into a 2. So there's error in this sort of approximation. But typically when we're using the SVD, there are so many variables and that we can use more columns and capture much more of the structure of the matrix. So the last thing I want to do tonight is I'd like to show you guys a little demo of how you can use the singular value decomposition to look at pictures. So we'll just keep going here. So Mathematica has a bunch of test images and test data already set up inside. So we're going to get a picture of an ocelot. So what we're doing right now is we're doing a little bit of Mathematica and image compression with the SVD. Okay. All right, so how are we going to start? Well, let's get an image. I is equal to, well, so let's bring in maybe, what did I say I wanted to grab? Oh, the ocelot, that's right. Example data, ocelot.jpg. All right, that's a nice looking ocelot right there. If you don't know what an ocelot is, it's a small cat. All right, so what is a picture? Well, a black and white picture is just a matrix. In fact, we could see that by, let's just look at a little piece of what's inside this thing. So if we took the image data, but we only want to take a certain piece of it, so we'll take the image data of I, and maybe we'll just restrict ourselves to the entries that run between 30 and 50, and the entries that run between 30 and 50, just to see what is inside that matrix. Well, you can see here that what we get is a 20 by 20 matrix of values. I shouldn't have used 20 values. I should have used something reasonable like 35, so we can actually see the structure of this thing. So an image is just a matrix. So the way that Mathematica thinks about JPEGs is as a list of real numbers. So numbers between 0 and 1. And the range of numbers between 0 and 1 tells you the intensity of the pixel that that particular position in the matrix encodes. So when you are looking at an image, what you are looking at is a matrix. In this case, I think it's a 200 by 200 matrix. So we could actually, maybe we'll take I data, and we'll set it equal to the image data from I. And then we could look at how big that data is by looking at dimensions of I data. And we find we have a 200 by 200 matrix. So this picture is 200 by 200 matrix of information that the computer is interpreting as an image. So the way image compression works is by throwing information away, redundant information. Now the method we're going to look at here is not the method that's actually used in practice for image compression. There's better methods, and for music as well. But the key idea of this is the same, which is that you look for important information and then you throw away redundant information. So we can do a singular value decomposition of this thing. So let's do the same thing we did before. U, S, and V is equal to the singular value decomposition of I data. We're going to suppress the output on that one. Okay, so what I want to do is I want to throw away some of the information inside U, S, and V. So S is a 200 by 200 matrix. It's got 200 singular values, and there's no way that the singular values of S are all important. Right? So here you can think like they're very, very fine differences in shades of gray, for example, would show up as very small differences in the small singular values. In fact, we can look at that if we just want to look at what S looks like between 1 and 10, and we put that into matrix form, we'll be able to see that the singular values start to die off pretty quickly. So there's one really important singular value. And then these are actually still pretty sizable, but by the time you get down to the end of the matrix, like if we looked at entries 100 to 110, so a little block matrix on the diagonal there, now we have very small numbers as singular values. So small magnitude of singular values is just like small magnitude of eigenvalues. It means that the information associated with that is not actually contributing very much to the structure of the big matrix. So here's a trick. We're going to do the same thing that we did up here with this little matrix, and we got this approximation that was almost the same as T, but kind of a crappy approximation. And we're going to do it to the matrix that represents this image. So we'll take U small now is going to be equal to U, and then we just have to pick how many columns we want to work with. So this is a 200 by 200 matrix. Let's see what happens if we throw away 150 singular values. It's a lot of information we're throwing away. Let's just toss some columns. So we'll write down U as being all rows, but now columns 1 to 50. Same thing with the singular values. But here, remember, this is square. And then finally, our small version of V, which is V all rows and columns 1 to 50. Now we've thrown a lot of, oops, should have suppressed that. So we've thrown a lot of information away by doing this. So let's see what this looks like in comparison with the original picture. I mean, I've just thrown away 150 singular values. I threw away 150 columns from one matrix and 150 columns from another matrix, and a whole bunch of that square matrix S is just gone because I only took the block in the upper left-hand corner. But when you put this all back together again, and then you wrap it back in the image command, which puts it back together into a picture that can be drawn, we get pretty close to the original image. So we've thrown away an enormous amount of information here. If you don't believe me, the dimensions of u small, that's 200 by 50. I threw away 150 columns worth of data. And the image that I got out here is pretty close to the image that I started with. It's not perfect. Of course, I did throw away quite a bit of information to get here, and you can see where that is, where that has an effect on the picture. So we have artifacting that happens all around the ocelot. If you've ever seen a compressed image that has artifacts in it, this is where they arise. When you throw away too much information, then you don't get smooth transitions between different areas. But as crude as this method is, it illustrates one of the big ideas of what the singular value decomposition does, what it can be used for, which is that you can use it to approximate a much more complicated matrix with a much smaller amount of information. So where this comes up in data science is in the reduction of the dimensionality of a system. So you have zillion variables and you want to identify what the important ones are. This is a way to do that. And not just what they are, but in combination. Now, if anybody's interested in how image compression is actually done, you can feel free to ask. I'd be happy to walk you through what JPEG is actually doing. The theme I'm after here is that the singular value decomposition is representing a matrix in an approximate way that captures most of the structure of the original matrix, but with much less information. All right, so there are some more exotic applications of matrix methods in Mathematica and some commands you might not have seen before. There's a million applications for what we talked about today, both block matrices and the singular value decomposition. I'm looking forward to questions you might have about this. And please engage with the homework, and I'll talk to you soon. Take care.